Howdy folks, and welcome to lesson 3.64 Geometry. Perpendiculars and distance is the topic at hand today. Talking about how to find the distance between a point and a line, what equidistant means, and distance between parallel lines. That will be the majority of the time spent on the lesson. We'll be finding the distance between parallel lines. Make sure you use those extra examples in your book. The ones I use here are similar to, but not exactly like the ones you see there. So let's get started on filling in these blanks here. So the distance from a line to a point not on the line is the length of the segment perpendicular to the line from the point. So there's the definition, but let's put that to practice here in some examples, or see what that looks like in these examples. So in the pictures below, draw a segment that represents the distance from P to line AB. I'm going to actually get out a protractor here and show you how to do this precisely, how to do this as accurately as we possibly can. That's what I'm looking for there. So I'm going to move my protractor around, and I'm trying to do this, draw a line, or draw the distance from a line to a point not on the line. Here's my line. I'm trying to draw the distance from P to that line. It's not going to be like this. Don't draw this in. It's not going to be like that, because that's not perpendicular to that line. The shortest distance is what we call the actual distance, quote unquote, from the point to the line. So that's not the distance. It's the perpendicular distance is the distance from the line to the point. So how can we find that? How can we make sure it's perpendicular? Here's the easiest way, I think, to do that. So take your protractor and spin it around until you've got the the 90 degrees lined up with the line itself. So I need to spin mine around just a little bit more. That looks pretty good right there. And now I'm going to line it up with 0 degrees with the point. So there it is. 90 degrees is lined up with the line. 0 degrees with the point. I'm going to draw a mark out here where I see 0 degrees. I'll get rid of my protractor now. Move that off to the side here. And now I'm going to connect this point to there with a straight line, with a line segment. So from here to there, why don't I get out my blue color though? From here to here, and I'm not talking about that whole thing, so I can shrink this down like that. So right there, that's the distance from point P to line AB, and that is because this is perpendicular to this segment, perpendicular to that line. It's the shortest distance from P to AB if it is perpendicular. So let's do the same thing with this one. So I'm going to line up AB with the 90 degrees and connect it to P. That looks good. And then I'm just connecting P to AB just like that, right along the edge there. This one happened to be horizontal, so yes, this could be vertical, and we'd have that distance right here. So here the distance is represented by that segment because this is perpendicular to this. So the distance from P to AB, line AB, in this case represented by that segment. And then finally over here, do the same thing, the same process. I'm going to try to line up 90 with line AB. Looks like I got it there, but then I need to line up 0 with P, and so I have a little problem here. It doesn't go to P if I just do something like this. If I moved it out here, then 0 would touch there, so it looks like I'm going to have to actually extend my line out here. So if P, the perpendicular distance from P to AB, doesn't actually touch line AB, you are allowed to do this, to think of it like this, to extend this out farther. So assume that this line goes out farther than what you actually see. This segment goes out farther, and keep it perfectly straight there. So this is going farther there. That means now I could line this up right there, and so that point going to touch right there. So if I connect that dot to that dot, that should do it for me. And then I'll just shrink that down. Come on. Where'd you go? There we are. And there it is. So right here, this is going to be my distance from P to AB, this segment right here. It's kind of messy, but that's okay. I just want to make this a little darker, a little bolder. That's the segment in question here. So this is the distance from P to line AB in that case. Moving on to these other definitions, two coplanar lines are parallel. Definitions and theorems. Two coplanar lines parallel if they are equidistant. So this is what this word, or where this word comes into play here in this lesson. So anywhere the two lines are connected with a perpendicular line. So if I connect, for instance, these two lines that seem to be parallel, if I connect them with a perpendicular segment, and I connect them with another perpendicular segment, if they're equidistant, and I could connect them with more if I wanted to, I could write all kinds of segments in there, perpendicular segments in there. If this is true in every case, wherever you go along these two parallel lines, the perpendicular segment connecting them is the same, in other words, is equidistant, an equal distance away, then you have two parallel lines. So that would mean I could do this on the picture. I could draw that in right there and right there. And why don't I actually use my other color for that? So I'm saying if this is true to start, all the perpendiculars are congruent to start along those lines that are apart that look parallel, you can actually assume that they are parallel. And then in a plane, if two lines are equidistant, it's the same word here again, if two lines are equidistant from a third line, then the two lines are parallel to each other. So what's that mean in the context of a picture? I'm saying that if they're equidistant here and here, so if these distances are the same, so in other words, we're saying they're perpendicular and congruent, if that's the same here as it is to here, they're perpendicular, they're equidistant from a third line. This is the third line, and then this line and this line are the two lines in question. They're equidistant from that same third line. That means they're parallel to each other. So in red, I could add the fact that this then would have to be true by this theorem right here, by theorem 3.9. So let's move on and check out some examples on the coordinate plane now. I can get rid of my protractor here. Find the distance between the lines x equals -3 and x equals 2. So I'm going to get out my line tool here, if I can. And there we go. So x equals -3. That means it doesn't matter what y is, x always equals -3. So if I go back to -3, y could be 1, 2, 3, 4. It doesn't matter. X always equals -3. So here's one line. I think I want to make that a little bigger, or a little thicker. So x always equals -3. That's better. And x always equals 2. So the same sort of deal here. Here's where x is 2. Doesn't matter what my y value is, x always equals 2. So here's another line where that's the case. So these are pretty easy ones because you've got vertical lines here. The distance is going to be the horizontal distance there. So these lines are parallel. They have the same slope. They're both undefined sloped. They're undefined slopes. And so the distance is going to be right here. I'll do that in red. So from here to here, that'd be the distance. So how long is that horizontal segment right there? You just count it up, really. -3 to 2, that's going to be a jump of 1, 2, 3, 4, 5. So what's the distance in this case? The distance is going to be, if you wanted to use numbers, you could say this is like -3, this is 2, so you're doing 2 minus -3. Rather than doing the hops, you could do that way. The distance would be 2 plus 3, which would be 5. And so that's the length of, we're saying this is perpendicular here and here, that's the length of this segment right here. If I use this with horizontal lines now, so now I'm saying that y equals something. This is tricky. No, didn't get it. I can do this, I promise. There we go. Got it. Beautiful. So we've got y equals -1.5. It doesn't matter what x is. If y is -1.5, that would look like this. So this is -1, -2, so halfway in between there, looking something like that. That's y equals -1.5. 2.3, doesn't matter what x is, y is always 2.3. So here's y is 2, here's y is 3, going a little less than halfway up there. So that's pretty close right there. So I'm looking for now this horizontal, or this vertical distance between these two horizontal lines. These have the same slope. They both have a slope of 0, so I know they're parallel. The distance is just going to be the perpendicular distance between those two parallel lines. So right here, the distance is going to be, it's a little harder to count the jumps here. We do have to deal with the numbers. So I just go with the bigger one minus the smaller one. That way I don't have to think about absolute value. So the bigger one is 2.3. Sorry about that. Let me erase my 2 there. So 2.3 minus -1.5 is the same as 2.3 plus 1.5. That is 3.8. So right here, that segment has a distance of 3.8, or a length of 3.8. So that is the distance between these two lines. Now let's do a slightly harder problem here. So find the distance between the lines. Now these aren't just horizontal or vertical. They're on a slope of some sort. This one happens to have, or these two happen to have a slope of 1/2. So there's going to be a process that we need to go through when dealing with problems like this. We'll practice a couple of these together here, and you should be graphing as you go. So let's start off with the graph of these two lines. Let's call this one, I'm going to color code some things here as I go along. So this one I'll put in blue. I'll say this is line L. This one I'll put in green, and I'll call this line M. And then the perpendicular line I'll use red for, and I'll call that line P for perpendicular. So let's graph this one. We have a slope of 1/2 and a y-intercept of -2. That means I can graph it. It should look like this. So let me get my line tool out here again. Alright, I'm using blue for line L. -2, it crosses right here, and every time I go up 1, I have to go right 2. So I'm going to have a point here, I'm going to have a point here, I would have a point down here. So this would go like this. So there's crossing through -2, it's going up 1 every time I go right 2. There's the blue line, line L right there. And then this one, I'll draw in green, y equals 1/2 x plus 1, same slope but different y-intercept. So it's going to cross right here instead, and then I'm going, every time I go up 1, go right 2, up 1, right 2, there is line M. So I'm just going to write that equation off to the side here. This is 1/2 x plus 1, and this one is y equals 1/2 x minus 2. So the perpendicular line to that, we're trying to find the length of the perpendicular segment connecting those two parallel lines. They're parallel because we have the same slope here. So let's start talking about I'll use black for the instructions on this. So first, let's start talking about line P. We've graphed the equation for L. We've graphed the equation for M. So now we're going to try to write an equation for line P, the perpendicular line to these things. So first, write an equation of line P that is perpendicular to both L and M. So as promised, here we go with red for line P stuff. So line P, the slope of line P, the slope of the perpendicular line to these two parallel lines is going to have the slope that is the opposite reciprocal of 1/2. What is the opposite reciprocal of 1/2? You flip that over, it's 2/1, which is 2, and this is positive, so that means the opposite reciprocal would be negative. So this would be -2 reduced is the slope. This is the opposite reciprocal again of positive 1/2. And then I'm going to use point slope form here. That I think is the best way, the easiest way to do something like this. So points, well, I'm going to pick a point on the blue line. So I'm going to start with line L here, that y equals 1/2 x minus 2. So I'm going to pick a point right here. I know this could be a point on my perpendicular segment. And so from there, if I'm going to go from there and have a perpendicular line, I'd be going up 2 and left 1, or I could think of it as down 2 and right 1. There's actually something in here that I wanted to change. It looks like it didn't get changed before I made the video. So I wanted to change this to 1/2 because I want this first one to be a little easier to deal with number-wise. And you might say, how is changing that to a fraction easier to deal with number-wise? Trust me, it will be. So this right here, now it's crossing at 1/2. I meant to do that earlier. So notice I just moved that down. Let's put this right here over 2. So 1/2 x plus 1/2. That's this green line right here. We should be good to go with everything else so far. So I want to choose a point. I'm picking the y-intercept of the initial line, the first line L. You could pick the y-intercept of the second line or the other line that's listed. Really, I would do whatever's easier to deal with. This one definitely is easier, in my opinion, to deal with because it's an exact value, no fractions that have to be dealt with here. So this is 0, -2 right here. And I am moving, let me draw in my line from there. And yeah, I'll make this one a dashed or hidden line. So I'm moving down 2, right 1. That's a slope of -2/1. Nope, I want to use red. Here we go. And I can think of that as being the same thing as going up 2 and left 1. So there's my perpendicular segment. And what I'm really looking for in the end here is the distance or the length of this segment in particular right here. So what's the segment from here to here? What is the length of that solid part of line P? So I can use a point. I can use the point that I see here. I'm going to call that my x1, y1. This is a point that is on that line. So pick one of these y-intercepts, pick the easier one to deal with. In this case, this is definitely the easier one to deal with. So we will use 0, -2 for my x1 and y1. This is my slope. This is my m value. It's not line m, it's the slope value of the line P. And so from there, the equation is going to be in slope or in point slope form. Y minus y1 is y minus -2. That's going to equal, the slope is -2, so -2 times x minus x1, which is 0. This would become y plus 2 equals, and the 0 would drop out, so I just have -2x. And if I subtract 2 from both sides, I've got y equals negative 2x minus 2. So this is an equation. It's not my final answer, but it's very important. It's a very important bit of information there. So I use this point, and I use this slope to come up with an equation for the line. So that means the equation for this line P is represented by y equals negative 2x minus 2. So from there, I am now going to do this step. So next, use a system. So first we did this. Next, we're going to, what? A system? Yes. From Algebra 1, you learned about systems of equations, or you should have learned about that there. So next, use a system of equations. You thought you'd never see that again, huh? Wrong. Next, use a system of equations to determine the intersection of, we're going to determine the intersection of M and P. So down here, this was the y-intercept of L. So we got this point already. Now we're trying to figure out this point. It looks like it crosses right on the grid lines. It looks like it crosses right at -1, 0, in other words. But we need to verify with that. We need to make sure that we're not off by like a tenth or 0.1 or 0.2, something like that. It is possible that that might not cross right on the grid lines if you haven't thought about the slope yet, especially. So let's see. Let's see what happens. So line M, the equation for line M again was this, 1/2 x, or y equals, I need to put that first, y equals 1/2 x plus 1/2. And the equation for line P, we found right here, it was y equals -2x minus 2. And so notice that, I'll go with purple now. I notice that this right here, and then in red, this down here, they both are equal to y. Y is equal to two different things. If y equals two different things, those two different things must equal each other. This equals this, and that same thing equals a third thing. That means the first thing equals a third thing. We can use substitution, in other words, since they are equal to each other. So let's write that down. Since both expressions equal y, why don't I use black for this? It's kind of my steps here. So this, I have nothing against purple, I promise. So since both equations equal y, we can set them equal to each other. And again, that is substitution. So I'm substituting -2x minus 2, since it equals y, I'm substituting that in place of y right up there. So I would have this equation then to go from there with. So now I'll use purple. I'll bring the purple back. So we've got 1/2 x plus 1/2 is going to equal -2x minus 2. We're going to solve that for x from there. So it looks like I could, trying to get x by itself, I could add 2x to both sides, subtract 1/2 from both sides. So if I add 2x, subtract 1/2, subtract 1/2. To save ourselves a little bit of writing, let's talk about this just mentally here. So this would be 4x over 2 is equal to the same thing as 2x. I just multiplied the top and the bottom is like over 1. So it's like 2 times 2 is 4x, or 2x times 2 is 4x. 1 times 2 on the bottom would be 2. So 4x over 2 plus 1x over 2 would be 5x's over 2. These would cancel. So would these. And then you have, this is like -4 over 2 minus -1 over 2. that is negative 5 over 2. And to get rid of the 5 halves here, to get x by itself, we could multiply by the reciprocal of the fractional part I see there. So I could multiply by 2/5. Got to do the same thing to the other side though. If I do that to one side, I've got to do that to the other side. And the nice thing in this one is everything cancels except for the x itself. So this is going to go away. That would just be a negative 1 left over. So you have x equals negative 1. So it does in fact end up working out on this one that that point right there is negative 1. And the y value at that point, let's see if it actually is 0 as it appears to be. So if we plug in negative 1 into the equation for line P, because I know this has to be on line P, whatever that point is right there. If I plug in negative 1, do I get 0 like I seem to notice that it will be, or that it should be? So let's find out. So y equals negative 2 times negative 1 minus 2. I just plugged in x right here, and I've got y equals, this would be 2, negative times negative is positive, minus 2, so y equals 0. So that in fact is the point right here. Let's label that point, and let's call it what it is. This is negative 1, 0. So that's, first we found the equation for line P. Next, we used a system of equations to figure out a second point, or where the second point crosses the other line. So right here we just picked the y-intercept, made it easy, but then right here we had to make sure it was actually crossing where it looked like we thought it was. And then finally we need to find the length of this segment right here. What is the length from there to there? So we're going to use the distance formula to figure that out. So finally, use the distance formula. To find the distance between those 2 points, the distance from negative 1, 0 to 0, negative 2. So to find the distance from negative 1, 0 to 0, negative 2. So here the distance is going to be, it's your, if we were to label these, why don't I actually do that here? I usually go left to right, call my leftmost point x1, y1, and I call this one x2, y2. So if I plug these things in, these are points on the red line, so I'll use red here for this. So we're saying the distance from there to there, the length of that segment is going to be, it's the difference in the x values squared. So it's x2 minus x1, we've got 0 minus negative 1 squared, plus the difference in the y value squared, negative 2 minus 0 squared. And from there, looks like we've got 0 plus 1, which is 1. And we've got negative 2 minus 0, which is negative 2. We're almost there. Looks like we got 1 squared is 1, negative 2 squared is 4. Add them together, you got 5. So this is the square root of 5. And if you wanted to use the Pythagorean theorem instead, really you could, because this would be 2 squared plus 1 squared equals hypotenuse squared. And you would solve it and get the same thing. But sometimes these numbers won't be quite so nice to deal with. We'll see that in our very last example in this one. So this would be acceptable. If it said rounded to the nearest hundredth, this would be acceptable. So this is an exact answer, the square root of negative 5. This is an approximate answer, rounded to the nearest hundredth, 2.24. So that's the distance between these two lines, these two parallel lines. Distance, remember, is always referring to a perpendicular distance. So this is perpendicular here, it's perpendicular there as well. So right here, the length of that segment is the square root of 5, or approximately 2.24. So from there, let's do one more example. Let's see what we got on this one. So that was a little tougher one. I wanted to show you one more example of that. We won't be writing these black instructions in on this one. We'll just go right into it. So on this one, I'll keep the same color coding going. So let's call this one line L, and this one, oops, line M. We're finding the distance between those two lines. So it looks like these two are both negatively sloped. We're going to be running downhill as we move left to right. We would have, let me get my line tool out here. The blue one, crossing at -3, and every time you go down 3, you go right 1, or if you go up 3, you go left 1. So we would have points. I could connect this point to that one right there, and then it would go up like that. It would continue going up in that same way, and it would continue coming down in this way. It's going to cross right there if that graph extended out farther. And then in green, let's draw that green one in. So crossing at +3/2, that's going to be, here's 1, here's 2, 3/2 would be halfway in between there, and still a -3 for the slope. So we would have right here, thought I had that in green, just a second. There we go. So every time you go down 3, 1, right there is halfway in between there, another halfway in between, there's 2, here's 3, and we would go right 1. Do the same thing, go down 1, 2, 3, and go right 1. Here would be another point, and going this way, we would extend that idea coming up. So it's crossing -3/2, and we'd have another point right there. So this is going to be line L. Right here is line L. In blue, there we go. And right here is line M. So what are we looking for? We're looking for the distance. So we're looking for, in other words, the perpendicular distance between those 2 points. I'm going to go with the same thing I did last time. I'm going to start with the y-intercept right here. I'm going to come up with an equation for that line that would be perpendicular to the 2 lines shown here. So let's look back at our example here, our first example, line P. Find the slope, find a point, and then use point slope form to find an equation for that line. So I'm not going to draw or write the instructions out again. Let's just start with line P. What's the slope of line P going to be? Since this is -3 for both of these, that's like -3/1. So if I flip that over, it's like 1/3. And this is negative, so that's going to be positive. This is going to be the slope of line P. It's the opposite reciprocal of -3. The point, or a point, on a perpendicular line connecting these two could be this point right here. I could really go anywhere along the line I wanted to, but I want to pick something that's easy to deal with. So right there, this is 0, -3. I know that point is on the line because that's the y-intercept of line L. So I'm going to go with 0, -3 as my x1 and y1. This is my m value, the slope value for that. So back here, we were saying use the y-intercept of L. I'm going to do the same thing here. I used the y-intercept of L. I could have used the y-intercept of m, but I'd rather deal with this number than a fractional number. So the equation for this is going to be y minus y1 is y minus -3, m is 1/3, and x minus x1 is x minus 0. This is y plus 3 equals 1/3 x. Subtract 3 from both sides, and you've got your equation for line P, the perpendicular line connecting those two. So let me draw that line out now, and I'll go with the hidden line for this for now. So from this point, I would be going get that in red, be going, oh come on, red. There we go. You'd be going up 1 and then right 3. Up 1, right 3 more would be just off the graph there a little ways. But I don't need to go that far with it. Just need to make sure it's going through 1, right 3, going through that point right there. If I went the other direction with it, going down 1 and left 3, so going like that, there would be a good equation for that line right there. And then from here to here, this is really what I'm looking for. This is what I want to know. What is the length of that particular segment right there? What is the length of that perpendicular segment connecting those two parallel lines? So I'm looking for this distance from here to here. This does not look like a very nice point right there. I don't know exactly where that is. It's a little more than 1, but it's definitely less than 2 in the x direction. And in the y direction, it looks like it's more than 2 or -2, more negative than -2, but less negative than -3. So I'm not sure what that is, so I can't just do a squared plus b squared equals c squared because I don't know how long a and b are. I know where this point is. I know that clearly is at 0, -3. But now I need to calculate the coordinates of that point right there. So how do I calculate those coordinates? Same thing we did before. Here it worked out really nice. We got a nice clean number. It doesn't look like we're going to get such a nice clean number on this one. But the idea is the same. So line M that intersects line P right there. This is line P. We're trying to figure out where does that intersect. So we could figure that out where these two things intersect by setting up a system of equations and solving that system of equations. We've got y equals -3x plus 3/2. And for line P, we have y equals, that was 1/3 x minus 3. So just like before, I'm saying this one and this one can be set equal to each other since they both equal y. So we would have -3x plus 3/2 equals 1/3 x minus 3. We're trying to solve this for x. And so from there, we're going to have some fractional values to deal with. It looks like if I add 3x, that would keep the x's positive. And if I added 3, that would keep the integer numbers positive as well. That would cancel there and there. That would cancel here and here. So really what I have here is 3/2 plus, to get a common denominator with 3, that's like 3/1. So this could be written as 6/2 is the same thing as 3/1. And then this would be 3x, that's the same thing as 9x/3. That gets a common denominator with what I see here. That's like 1x/3 is the same thing as 1/3 x. Combining like terms gives me 9/2 equals 10x/3. And in order to get x by itself, I would multiply by the reciprocal of the fractional component of that expression. So times 3/10 on both sides would get rid of the 10/3 right there. That gets me x by itself. X then equals, this is 27 on the top over 20 on the bottom. So was it a very nice number? I would say no, not at all. 27/10 could also be thought of as x equals 2 7/10. So let's see, does that seem to, not 2 7/10, it's 1 7/10. Or 7/20, excuse me. So 1 7/20 right here. We're saying that x, if I go over 1 7/20, yep, that looks like a little less than halfway. 10/20 would be halfway. So that seems to match with what I see right there. And so what's the y value that corresponds with that? We got to plug it back in for line P. We could use line M as well, but I'm going to go with line P. I'm looking for that coordinate right there. Either would work, plugging them back in. So this is going to be y equals 1/3 times, I'm going to use this because that's easier to deal with when I'm multiplying fractions than a mixed number. So 1/3 times x is 1/3 times 27 over 20 minus 3. That means y equals, this I could get to cross cancel. I could say this is a 1 and this is a 9. Dividing both by 3 gives me that. And so this is 9/20 minus 3. If I write that as something over 60, that would be, not over 60, over 20 is what I meant to say. It's going to be 60 over 20. And so from there, I've got what I'm looking for. This would be negative 51 over 20, or you could think of that as negative 2 and 11 over 20. 20 goes into 51 2 whole times with 11 left over. So that's my y value right here. So all that to say is that this point right here is 1 7/20 for the x value and negative 2 and 11/20 for the y value. I'm going to use this point and this point just like before with the distance formula. I'm going to plug it in and see what that length is at this point. So this is going to look like, what color did I use there? I'll keep it consistent. I'm using red. Yep, because I'm finding the distance between that point and that point. So the distance is going to be, I'll call my leftmost point x1, y1. My rightmost point would be x2, y2. And then I am doing the difference in the x values. So it's 1 7/20, or going back to the improper fraction style because it's easier to deal with when I'm adding, subtracting, multiplying, dividing. This is 27 over 20 minus 0 squared, the difference in the x values there, plus the difference in the y values squared. So the negative 2 and 11/20, that was negative 51/20. Make that negative sign a little easier to read there. We have that minus negative 3. And all that is squared. So this becomes 0. I don't need to think about that. It's just 27 over 20 squared plus, and this is like negative 51 over 20 minus a negative is positive. This is like 60 over 20 is the same thing as 3. So we have that squared. 27 over 20 squared is going to be 729 over 400. That's 27 squared over 20 squared. And then this would be, looks like 9 over 20 squared. Negative 51 plus 60 is just positive 9. And then that becomes 81 over 20 squared, which would be, or 9 squared over 20 squared would be 81 over 400. So I've got 81 over 400. That means I have the square root of 810 on the top over 400 on the bottom. And I'm not going to make you write that or try to write that in a simplified radical form way. We're just going to approximate it. And if you type that into a calculator, you get about 2.01. That is the distance, folks, right there, of, or the length of that particular segment, the solid portion of the segment. So this length is approximately 2.01. So there's a lot going on there. Make sure you study that, review, and rewind as needed. But make sure you can do a problem like this. If you're one of my students, expect to see something like this on the quiz. Not one where there's quite as many fractions to deal with like this. I wanted to just give you a little extra challenge one here. See if you can get this one. If you could get this one, you should definitely be fine for our upcoming test when a question like this pops up. But definitely expect to see one like this. We'll have nice integer values to deal with. but you'll have to use the process, show me that you understand the process, and go through it all to find the distance between two parallel lines on the coordinate plane. Also, make sure you know how to find the distance if it's just horizontal and vertical. That's much easier than what we did here. This is not hard, I don't think. It's all stuff you've done before, but we're putting together all these ideas that we've learned before in a more prolonged way, you might say. And so again, with example 1, make sure you also know how to do things like this, that you know that the distance between a point and a line is going to be always that perpendicular distance between those two things. That does it for us for this lesson. Review, rewind, and comment as you find fit. If you see any mistakes, let me know. As always, like the video if you liked it and you found it helpful. Have a great day, and I will see you later for our next lesson. Adios, amigos.